All right, now that the recording is up again, so let's continue our session and talk about the caching basic, right? Because caching is a big part of the memory hierarchy, and we need to figure out what's the best way to design these caches, right? But before we go there, let's go with some basic definition first so that we can use this definition. And if you want to look up like more material from the internet on read papers for our reviews so that you see this terminology, right? Caching basically try to take advantage of two things. First is temporal locality, right? Temporal locality. For example, if you have code like this, for, right? I equals 0, I is less than 100, I plus plus, right? So that's our code. And then in here, I just do A of I equals I. If you look at this code, are there any variable that get used over and over and over and over and over again? What is a variable that gets used all the time here? So what gets used all the time here? You have the beginning of your array, right? The A and the I. We use A and I all the time. Temporal locality, the way you remember this is temporal is time. So temporal locality basically means that if I use something, if I access some data, I will likely access the same data again in the future. So the best policy for these guys is, well, we just keep them in the cache. If I access something, I put them in the cache, right? So the paper was introduced in 1965, and as you can see, it's a long time ago, right? More than 50 years ago, actually. And then modern day cache also take advantage of spatial locality. So three years afterward, right? There's another different paper at the IBM System Journal that look at the same program. You look at the same program, right? The first loop, the first time you go into the loop, you access A0, right? What's the next thing you access? You access A0, the next thing is A1, right? So what's the next thing? Now I'm going to let you answer. What's the next element in your array that you will access? I guess here. So what's the double? A2, right? Yes, it's actually that simple. This is called spatial locality. Spatial is space. If you access something, there's a high chance that you are going to access the thing next to it, right? Close by data is likely to be accessed soon in the future as well, because that's how we program, that's how we think, right? So again, many of the things we do in hardware reflects how you program, This is like a really common thing you do in your program. So caching is designed to take advantage of both of these things and use it to manage the data in the cache, right? So back in the day, one thing you can do is you can manually manage everything as a programmer, right? One thing I can do is to design a hardware that allow the programmer to say, hey, put this in the cache, put that in the cache, kick this out from the cache. This is painful for a programmer. And if you look at modern day program, no one does this anymore because now hardware is handling cache management. Except for some region of the GPU cache, which can be manually managed. The rest of it, the hardware will manage the data across all level. The programmer only have to deal with the memory access, memory reference, the address of your variable, right? But if I say that, hey, it's always managed by the hardware, why should you care? Why should you care? Well, first of all, because we are in architecture class, we should learn how this is designed. But if you know how cache work, you can actually write a program to make it more cache friendly. So you can write a program that are cache friendly. So a cache-friendly algorithm or a cache-friendly program, which is actually something that is done in high-performance computing all the time, will try to make sure whatever you try to access is already in the L1 cache. It's already in the L1 cache. Let me give an example in Thai, because we just did a long discussion about caching, right? คือ cache-friendly program เนี่ย มันจะเหมือนกับว่า เราหิวตลอดเวลา แล้วเราจะดีไซน์โปรแกรมโดยให้ make sure ว่าของที่เราอยากกินเนี่ย มันจะไปอยู่ที่ร้านป้านกทุกครั้งที่เราจะไปกิน อันนี้คือเป็นการออกแบบโปรแกรม การออกแบบอัลกอริทึมให้มัน cache friendly ก็คือว่าทุกครั้งที่ผมต้องการ data ตัวนั้นมันจะอยู่ใน L1 cache แล้ว ถามว่าประโยชน์คืออะไรครับ so what's the benefit of a cache friendly program? It's going to be faster because every time I need to access my data, I never have to go to DRAM. Or I rarely have to go to DRAM. I can always find my data in a fast memory in the cache. So your program gets faster. So now let's talk about some basic terminology of caching. So let's look at the load instruction. We talk all the time before the midterm, right? The size of the load and store from lab 1, right? You can have something like a load word. Load word, right? So let's say it's a 64-bit machine. If it's a 64-bit machine, one word is 8 bytes, right? Or 64-bit. You can also load a byte, right? You can also load a byte as well, right? So this is one single byte. These are the units of your load. You are loading up to 8 bytes of data. You are loading up to 8 bytes of data. But because we realize that, hey, that's spatial locality. If you access A0, you're likely to access A1, then A2, then A3, then A4. So instead of bringing in just 8 bytes of data, why don't we bring in something bigger, right? And that bigger unit, we call this a cache block. A cache block is typically larger than the size of the load, so that when you access the first elements, you get the rest of it together, right? So let's say you have that from the other, the earlier example, you have A0, right? A1, A2, and then say A99999, right? How big is an integer? What's the size of an integer? How many bytes is one integer? What's the size of an integer? Well, if you just declare like int a, how big is that? How many bytes is that? Four bytes. Thank you so much. So A0 is 4 bytes, right? But let's say my cache block is, let's say it's 32 bytes. In modern day processor, it's actually 64 bytes for your CPU. You can basically configure the size depending on your design. But let's say it's 32 bytes. So when you access A0, you bring the entire block, right? So A0 is here, right? What do you get afterward when you bring the entire 32 bytes? What do you get on top of A0? What else do you get? So this is 4 bytes, right? This is 4 bytes. And you bring A0 in, but because it brings the entire cache block, A1, A2, A3, A4, A5, A6, and A7 is now in the cache because the entire 32 block is now in the cache. So when I have to access A0, then A1, then A2, then A3, then A4, the first time it's not in the cache, I brought it in. When I access it again, A1, A2, A3, A4, A5, A6, and A7, they will already be in the cache, right? They will already be in the cache. มีคำถามไหมครับ อันนี้งงหรือเปล่า ก็คือ เวลาผมรันโปรแกรมอ่ะ มันก็จะ access A0 A1 A2 A3 A4 A5 ใช่ไหม แล้วด้วยความที่ว่า A0 มันแค่4 ไบต์ แล้วเวลา cache มันทำงานโดยที่แบบสมมุติเรา access A0 4 ไบต์เนี่ย มันจะดึงมาเลยทั้ง32 ไบต์ ดึงมาทั้งก้อน ซึ่งทั้งก้อนนะสมมุติตีต่างว่า A0 มันคือพาร์ทแรกของก้อนนั้นใช่ไหม A1 ก็จะเป็นพาร์ทต่อไปเรื่อยๆปึ๊บแล้วสมมุติก้อนนั้นมีขนาด32 ไบต์ แปลว่าผมก็ดึงมาเลย8 อัน A0 ถึง A7 นะครับ มันก็อยู่ในแคชบล็อกเดียวกันเลย เพราะฉะนั้นครั้งหน้าที่ผมต้องการ access A1 อ่ะ มันจะอยู่ในแคชแล้ว ตอนนี้ผมจะ access A2 ก็จะอยู่ในแคชแล้ว จะ access A3 ก็จะอยู่ในแคชแล้วนะครับ ก็นี่คือการทำงานของแคช มันจะสามารถ exploit a spatial locality กับ temporal locality ด้วยสาเหตุที่ว่าไอ้บล็อกนี้มันใหญ่กว่าขนาดของโหลดแล้วนะครับ so that's how that's why we have a cache block that is size a little bit bigger than a load, right? And when you access to a certain part of your program, you basically go access a part of the block. In this case, let's say A0, right? You then just go to the front of the block to get A0. Then you go to A1, then you go to the next part of the block to get A1, and so on and so forth, so on and so forth. We call a cache hit when your data is in the cache, and we call this a cache miss when the data is not in the cache. So in this case, A0 is a cache miss. But then you bring A0 to A7 in the block into the cache. So A1, A2, A3, A4, A5, A6, and A7 is now in the cache, right? It's now in the cache. And now you have a design choice, right? What do you want to store in the cache? You can store instruction. You can store data. You can store virtual address translation. We'll talk about this next week. You also have to think about how to place the data in the cache, right? Because cache is limited. You need to figure out what should you put in the cache. Let's go back with the cafeteria analogy in Thai because we were having the good naming in Thai, right? ก็คือสมมุติข้าวร้านป้ามีขนาดจำกัดคือป้าไม่สามารถซื้อกับข้าวมาตุนไว้ในตู้เย็นหมดทุกอย่างในจักรวาลได้ วิธีในการสต็อกของป้าควรจะทำยังไงครับถามน้องๆหน่อยวิธีในการสต็อกของป้าก็คือมันคือวิธีการในการเลือกว่าเราจะเอา data อันไหนไว้ในแคชงั้น policy ของป้านกต้องทำไงบ้างกับ policy ของ7ใน VISTEC ควรจะต้องทำไงบ้างไม่มีคำตอบที่ผิดนะก็คือมันต้องมี policy อะไรสักอย่างในการเลือกว่าป้านกจะซื้ออะไรมาเตรียมทำกับข้าวให้เราแล้วก็7จะสต็อกอะไรไว้ในเชลฟ์บ้างดีมากครับของที่ต้องใช้บ่อยๆอันนี้ก็เป็น policy ที่ดีมากๆอันนี้เพราะว่าเรารู้ว่าเฮ้ยช่วงนี้แบบเด็กชอบกินอะไรเดียกะเพรามากเลยข้าวกะเพราก็ไปซื้อตุนเลยใบกะเพรากับหมูใช่ไหมแล้วก็ซื้อแบบตุนพริกตุนน้ำมันหอยตุนของที่เราต้องเอาไปทำกับข้าวที่เด็กชอบกินกันเนาะ So that's about how to place the data in the cache, right? Then what else we have to consider? So when the cache is full, right? When the cache is full, what to kick? Because when the room is full, you have to kick someone out because the new data is coming in, right? So you have to figure out what should be replaced. Then when you have to modify the data, how do you synchronize everything to make sure everyone still have seen the most updated version of your data? Do you want to have a different granularity? Sometimes work with 32 bytes, but the block can be extended to 64. What should be the size of the cache block, right? And then the primitive cache design would have what we call the tag store. The tag store acts like a key. It stores the tags of your access, right? It stores the identifier that say, hey, this blob of data is yours, right? This tells whether your data that you are searching is in the cache or not. Then you have the data store. Data store is probably, as the name suggests, that's where you store the actual data, right? You store the actual data. So think of it this way. Think of it this way. Let's think of a cache as a big room, right? A big room. Let's say it's the theater, right? A theater. Let's say a cache is a theater. Then people can sit in a chair to watch a movie, right? So the data store is those chair that can fit, like people can sit in there to watch the movie. That's the data store. The tag store is the label for each chair. Row A, seat 1. Row A, seat 2. Row A, seat number 3. Row B, seat number 7. These are the tag store because you need it to figure out where's my seat, right? And basically, you use the address. You use the address of your access to index and search the tag store in order to get the data that you want, right? So what's in the tag store? The tag store would have the valid bit. The first thing is you need a valid bit. You need to figure out, hey, is that a valid data or is it some junk that just get initialized and this something that's not usable? Then you need the tag. The tag is the ID that allows the access to figure out, is that my data or is that someone else's data? Then you have the replacement policy bit. We'll talk about this later in the next week when we talk about the different replacement policy. This determines the likelihood of evicting this cache block. The dirty bit, again, I didn't want to talk, we will talk about this later in this class. But the dirty bit will talk about if someone modified my data, someone changed the data, how do you make sure that this is propagated to the L2 cache, L3 cache, and DRAM? So here's the organization. The cache contains multiple blocks, right? Let's say a block is 32 or 64 bytes. Your cache is likely like at least 1 kilobytes of data. So you have multiple blocks in a cache. Each block belongs to a cache set. Again, look at the theater analogy, right? Let's say your cache is a movie theater. You can think of a cache set as the row. You can go to row A, set A, row B, set B, row A, row B, row C, row D. And when you buy a ticket, you will have the row and you have the seat. So when you look at the ticket, you know right away which row do you have to go to, right? The ticket is the memory address. The ticket is the address. From the ticket, you can tell the row. So you know exactly where do you want to go, right? Each memory access is mapped to a certain set. So let's say we have one example of a cache over here. You have 7 sets, 16 blocks in total. So we have block 0, block 1, blah, 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 right? And as I said, these block would belong to one of the set, right? These block would belong to one of the sets. So in this case, if I have an address that access one of these blocks, like block 4, in this case, I will know from my address that I have to go to set number 2. And then from there, I search, hey, is that block 4? Is that block 4? Is that block 4? Until you find block 4 or until you search every entry in the set, every block in the set, and it's not there. Then you go to the next level. All right, so here's some example. Let's say you have, how big? 124 bytes hash, right? And then the cache block size is 32. And then there are 4 sets. Oops. There are 4 sets. So my question is, how many hash block do we have per set? All right, I'll give everyone here 2 minutes to work on this, but how many hash blocks per set do we have here? Again, we have this cache, right? This is 1024 bytes, right? And then one of the cache block is 32 bytes. And we have 4 sets in total. Set 0, set 1, set 2, and set 3. My question is how many of the boxes that we can fit in each of the set for the cache block. The way we do this, so let's say, let's assume you have the answer already. Now let's go through how do we approach this question. So you have in total, you have 1024 bytes, right? And each cache block is 32 bytes. So it means that, so 1024 is 2 to the 10, right? This is 10, this is basically 1024. 32 is 2 to the 5, right? This is 32. So 2 to the 10 over 2 to the 32 is again 32, or 2 to the 5. It means that in total, your cache will have 30, will be able to fit 32 cache blocks. You have 4 sets. You have 4 sets in total, right? So from here, you have 32 cache blocks. You have 4 sets. So in the end, you have 8 cache blocks per set. So over here, this diagram will be able to fit cache block 8 of these guys. All right. So basically, that's how you approach the question, or how you approach, like, how do you organize the cache? Now let's talk about the lookup. Let's talk about the case where you are hungry and you want to buy food, right? Using our analogy, your CPU needs data and it has the address, it wants to access that address. Then the address is divided into multiple set of bits. There'll be a tag part, there'll be an index part, and the way it works is this. So let's say this is your address, right? The leftmost, I typically call this the byte in block. The byte in block basically is a part of the address that tells you which of the byte in my cache block that I'm trying to access, right? So let's say your cache block is 32 bytes for the size. How many different locations do I have to be able to tell? I need to be able to tell from byte 0 to byte 1 to byte 2 to byte 3 to byte 31 of those cache block, right? So it means that I need log of 32 in order to tell which byte I'm trying to access, right? So let's say this is 32 byte cache block. So over here is going to be 5 bits. 5 bits. The next part, we call this the index bit. And then the rest are the tag bits. So the index bit tells you the set ID. Which set do you go to, right? So let's say you have some let's say example, right? Let's say you have 8 hash set. So let's say we have eight hash set. How many bits do we need for the index to be able to tell that set 0, set 1, set 2, set 3, set 4, set 5, and set 6, and set 7? How many bits do we need there for the index bit if we have 8 hash set? How many bits? So it's log is log of the number of sets. So in this case, it's log of 8, right? So in this case, it's 3 bits. The rest are the tag bits. All right, so that's our cache lookup. Again, how to get the index bit, each address to point to the unique bytes. So the cache block, again, usually 64 bytes for the CPU, but this can be different depending on your design. The last n bits will be used to actually tell inside the block which byte you're accessing. So you need log 2 of that. Then the next set of bits are for the index bit. So you get log 2 of number of cache set, and then the rest are the tag bits. So let's say, again, this is your address, right? This is your address. This is an index. This is a tag. This is going to be M bits. This is going to be N bits. And again, the rest of the address are the tag. All right. And because you can have different number of cache block per set, depending on the design, we have the name for some of these. The first thing is called direct map cache. The direct map cache means that the cache block only go to one single location. Also, by the way, it basically means that there's only one cache block per set. One cache block per set. When you have one cache block per set, that's a direct map cache. A load store can look up the tag using the index bit. So if the tag is matching, it means that data is yours. Otherwise, it's a cache miss. If it's a hit, return the data. Otherwise, go to the next level. So this is a question I want to answer later when we do a break. Is it possible if I use the direct map cache and I only go access 2 different addresses, but then I never get a hit? So let's keep that question when we do a break. The next type is called set associative cache. For the set associative cache, right, the problem with the direct map cache is when you have data access, they can be mapped to the same location over and over and over and over. So the solution is, well, why don't you store more than one cache block per set? More than one cache block per set. So the cache block is one single unit, right? And the cache set in this case will store multiple blocks. This is called set associative cache. The downside is when you have to look up, now you have to compare multiple tags. The set associative cache somehow is called the n-way cache. So a 4-way cache means that there are 4 cache blocks per set. 8-way cache means that there are 8 cache blocks per set. It's as simple as that. All right. And then you go to full-blown fully associative cache, which means that's one set. That's one cache set. Every cache block is in that set. Basically, you go in, the cache can be placed anywhere, and you search everything. You search everything. When does this work well? So when the cache are small and you don't have to compare a lot of things. But this can be the bad idea if your cache gets bigger, because now you have to search many cache blocks and see, is that my tag? Is that my tag? Is that my tag? To find your data, right? So now let's do a 5-minute break for the Q&A before we go into the how to insert and how to replace the data to the cache. All right. มีคำถามไหมครับ